Hello, my name is Yao Xiao, a PhD student at Stanford University working with Professor Colin Triple. I'm excited to tell you about our work on synthesizing formal models of hardware from RTL to support efficient verification of hardware memory consistency model implementations. This is joint work with our collaborators at Research. Let's consider a concurrent program where two cores share memory at address X and Y. Core 0 writes 1 to X and then Y. Core 1 prints conditionally depending on the values it reads for Y and X respectively. Is it possible for the program to print hello world? Yes, an example order is 0, 1, 2, 3. How about world? Yes, if it's execute, say 0, 2, 3, 1. Can it print nothing? Yes, an example order is 2, 3, 0, 1. This execution obeys sequential consistency, which requires outcome of a parallel program to be some in-order interleaving of instruction from program threads. Let's consider a counterintuitive result. Can the program print hello only? This depends on the memory consistency model or MCM of the hardware on which the program is run. For example, MCM on the left, such as ARM memory model, permits such result while x86 TSO and SC on the right don't. In this example, the MCM of the hardware on which the program is run ultimately decides what the program will print. More generally, MCMs restrict the ordering and visibility of shared memory accesses on a multiprocessor, and therefore the outcome of program. Given our example program, x86 TSO forbids reordering of store instruction that will lead to outcome being hello only. But MCMs such as our memory model allow such reordering. Since microarchitecture must correctly implement the MCM specified by their ISOs to correctly execute parallel programs, a question is, how do we verify a specific microarchitecture indeed implements a given MCM? To verify hardware MCM implementation, Pairwise proposed a suite of tools called the check tools. Given a processor design and a suite of litmus test program, the check tools formally prove whether the processor implementation complies with its ISA MCM with respect to the litmus test program. These litmus tests are small parallel programs featuring an outcome of interest to be checked by the check tool, such as hello only for the running example. Despite their success in identifying real bugs in processor, compilers, and MCM specification, a key limitation of the check tools is that processor must be supplied in the format of an axiomatic model called a MICRO' model. Therefore, deploying the check tools on real hardware is limited by a semantic gap between axiomatic MICRO' description and operational Verilog. This work resolved the gap by proposing automatic tool called RTL to MICRO' for synthesizing a MICRO' model of hardware from RTL design with minimal user intervention. In general, automatic synthesis of MICRO' models have the potential to unlock all the benefit of the check tools. Many of them conduct litmus test-based verification. Another tool facilitates MCM verification over all programs, and yet another conducts hardware security verification. However, all of them require MICRO' model as input. In this work, as first iteration, we demonstrate RTL to MICRO' support litmus test-based verification of hardware MCM implementation with pipe check, and therefore RTL to MICRO' currently synthesize a restrict MICRO' model that consider instruction relevant for MCM verification only. We plan to extend its functionality to integrate with other tools in the check stack that we just mentioned. Before explaining how RTL to MICRO' works, let's take a closer look at how MICRO' models are used and what they look like. The check tools leverage MICRO' models to conduct microarchitectural happens before all MHB analysis. The analysis is a flavor of Lamport style happens before analysis that reasons about observability of hardware level program execution. Suppose we want to determine if a processor like RISC-V multi-vScale implements sequential consistency. We will supply the check tools with the processor implementation and a litmus test in pseudo assembly program, such as one similar to the hello world shown earlier. The check tools needs to determine whether the program run on multi-vScale can ever produce such result where reading of X returns 0 and disallowed by sequential consistency. To do so, the check tools explore always the input hardware can execute the program, checking possibility for MCM violation. To facilitate this search, the check tools model hardware-specific program execution as MHB graph, one shown on the right, which encode an execution of input program having illegal result on the input hardware. Let's take a closer look. Column labels corresponds to instruction in the input program sequencing from left to right on each core. Row labels represent hardware state elements or collection of them within input microarchitecture. For example, DX represent the code execute stage of the processor to the left. Going inside the graph, a node represents an instruction updating some set of hardware state elements. For example, highlighted nodes represent instruction I1, which writes 1 to Y on the left, updated memory. The update happens before ages are used to model the ordering of hardware events. We observe that these ages are instantiated for a few reasons. First, some ages are localized to a particular instruction or column in a MHP graph. Such ages describe a partial order on the state updates for an instruction execution. For example, the red ages illustrate the store instruction, like IF1, updates first the IF stage, DX stage, and finally memory. Second, some ages represent ordering that result from instruction contending for shared resources. For example, both I0 and I1 on core 0 update the same DX stage. Therefore, the updates should be serialized. And the red age shows the ordering is that I0 updates DX stage before I1. Third, some ages encode ordering that result from communication via shared resources. On the left, the outcome of the interest indicate that I2 reached the value written by I1. Since communication between cores on this processor is possible only via shared memory, I1 must have updated the memory before I2 reads from it and updates the register file, and therefore the highlighted MHP age. A cycle in a MHP graph indicates an impossible sequencing of events where one event must have happened before itself. Therefore, to verify a litmus test, always execute correctly on a microarchitecture. The check tools search for the existence of an acyclic MHP graph corresponding to forbidden outcomes. Failure to find such a graph is a correctness proof. MICRO' models are what enable the check tools to conduct such a search. Specifically, it specifies the space of all possible MHP graphs that could be instantiated to describe hardware-level execution of programs on a particular microarchitecture. While both Verilog and MICRO' models describe microarchitecture, their semantics are completely different. Verilog models hardware operationally, specifying how state elements are updated on hardware over time. For example, a flip-flop in DX stage is updated with the value from another flip-flop in IF stage if processor is not stalled. In contrast, MICRO' model use a set of axioms in first-order logic to specify the ordering of hardware-level state updates that are enforced by a particular Verilog design. Concretely, a MICRO' axiom can specify when the low instruction is executed, it will update FFIF register before it updates FFDX register. In general, such ordering rules are not obvious in the Verilog. In this work, we resolved the semantic gap and answered the following question. First, what are the basic building blocks of complete MICRO' model? Second, how do we automatically synthesize a correct and complete MICRO' model from RTL? Third, can this synthesized MICRO' model support efficient MCM verification? To answer the first question, recall that a MICRO' model is essentially a set of rules on aiding MHP nodes and ages to instantiate hardware-specific program execution as directed graph. We refer to them as happens before invariants or HBI. The HBI can be divided into two types. Intra-instruction HBI describes state updates on behalf of an instruction execution along with partial order. In other words, intra-instruction HBI instantiate MHP graph columns. Inter-instruction HBI describe ordering between events that correspond to different instructions, thereby capturing hardware-level instruction interaction. Let's take a closer look at them. Intra-instruction HBI captures how instructions flow through the design by specifying for each instruction type the state elements updates by that during its execution and the partial order on these updates. For example, shown on the slide is a MICRO' axiom describing store word instruction on multi-V-scale processor. The axiom consists of 5 HBI, and one of them essentially says for all instruction being stored word, its update on SW in write-back register happens before its update on MEM. Inter-instruction HBI, on the other hand, specify ordering rules governing instruction interaction during their executions. There are several types based on the reason of interaction. First is structural dependency, specify ordering rules on state updates to common state elements that must be serialized. On the right, say two instructions on same core, both update the LW in write-back register during their execution. Since there is only one LW in write-back register, these two updates should be serialized and the order should be described. If this processor feature in order pipeline, an HBI in MICRO' axiom shows if instruction I0 comes before I1 in program order, I0 always update LW in write-back register before I1's update. On the other hand, if the processor feature out of order execution, the HBI might instead specify while two instructions must be ordered in their updates, the order will be determined dynamically, that is one way or the other. The other interaction type is data flow dependencies that specify the happen before rules when two instructions share data. An example axiom shown on the left-hand side gives that if there's a write instruction whose value are sourced by another read instruction on same address to update some other resource, say register file, there should be a happens before relation between the update to memory and the update to register file to enable this interaction. Now, with the knowledge of building blocks, we present an overview of RTL to MICRO'. We take in as input Verilog design, use commercial tool to parse it into netlist, RTL to MICRO', then analyze the netlist, generate a set of hypotheses, which are basically an over-approximation of all HBIs. The hypotheses are embedded as property to query Jasper Gold against Verilog design. Jasper Gold is a model checker that have solver as backend to explore all hardware traces to prove a property hold in a Verilog design. Finally, we collect only those proven HBI to have correct by construction MICRO' model in the end. Next, we give details on each of the steps. Our analysis starts with generating execution path. We observe that hardware level data flow is a type of happens before relation. For example, in Verilog, we may have a wire connection from SW data buffer register to memory data board. To have correct value being consumed by MEM, updates on SW data should happen before memory gets updated. Therefore, if one visualized in data flow graph, we have register being mapped to nodes and edges being drawn to capture this flow of data from one register to another. Moreover, if one proves an instruction, say store word operation, updates both SW data and MEM during its execution, then according to this data flow implied by the wire connection, we essentially have a happens before invariant as part of store word instruction execution path. With this, we can do so for every possible data flow relation in the RTL design and extract subset of data flow relation for each type of instruction. And this forms the way to extract instruction execution path. Specifically, since full design data flow graph of RTL design contains all possible data flow relation that can be induced by instruction in the ISA. We start with the generation of it, where nodes are registered and edges being collapsed of combinational logic. Next, for each instruction type to be included in the final MICRO' model, such as load and store word instruction for conducting MCM verification, we identify subset of state elements in the full design that can be updated during their execution. To do this, for each type of instruction, we generate an intra-instruction HBI hypothesis for almost every register in the full design DFG. Each hypothesis query Jasper Gold whether an instruction is capable of updating, or in other words, capable of changing the value of a particular register when it executes. One example asks whether the register file can be updated by load instruction, as illustrated on this slide. In the current implementation of RTL to MICRO', we make an assumption called the single execution path assumption, that each instruction always updates the same fixed set of state elements during its execution. Hence, for example, hypothesis shown on the right, if it's proven to hold on this input design, RTL to MICRO' will interpret this result as load instruction always updates the register file. We instantiate hypothesis in system Verilog assertion form to query Jasper Gold against Verilog design. For our load and register file example, Jasper Gold will explore always load instruction can execute to check to see if it can ever induce a state updates on the register file. Jasper Gold will find that the load is indeed capable of updating register file during its execution. Therefore, register file is included in the set of state elements which are deduced to be updated by loads. We prove the same hypothesis against store instruction and guided failure. That is, store instruction never updates register file, and therefore we don't have register file in store specific set of state elements. We do so for every node in the for design DFG for each instruction type, so that we have a subset of state elements proven to be always updated during its execution. Implied by the for design DFG, we can then include ages if both ends are in the per instruction updated set of state elements. Subsequently, we will have per instruction DFG, where data flow relation proven to always happen during an instruction type execution. Since data flow is a type of happens before relation, we also arrive with a proven set of intra-instruction HBI through one-to-one mapping from per instruction DFG. One familiar example is the WData and MEM data flow always happens, and therefore an HBI included in store word execution path. Now per instruction DFGs have all hardware events happening on behalf of an instruction. Hence, we can pairwise compare this subgraph to enumerate all potential instruction interaction via state elements. Take structural dependencies, for example. Since it is defined as serialization due to access to common state elements, pairwise comparison looks for same state elements in both graphs. As mentioned before, an ordering on the two updates should be specified. In our case, we generate hypotheses to get the ordering with the help of Jasper Gold. Concretely, the ordering hypothesis asserts if two instructions come in some order, say program order, do the two updates on the same state elements always happen in the same order? One example is if load come before store instruction in program order, do their updates on the data preserve program order. Once again, we embed the hypothesis as property to query Jasper Gold. Jasper Gold will explore all hardware traces to see if property holds for the design. If Jasper Gold proves the property, we have HBI saying if instruction load come before store in program order, its update on WData happens before that of store. Similarly, we can do so for data flow dependencies as well, where the pattern and the property instantiation are slightly different. Due to time constraint, we will not go into details. But on a high level, this step generates us proven ordering rules on instruction interaction. Finally, we collect these proven HBIs to arrive with a proven correct by construction MICRO' model in the end. Now let's take a look at case study. To showcase the efficacy and efficiency of RTL to MICRO', we verified the RISC-V multi-V-scale processor MCM implementation. The multi-V-scale is a 4-core RISC-V processor featuring 3-stage in-order pipelines and implements sequential consistency. For RTL to MICRO', we have correct by construction MICRO' model that can be used in check-based MCM verification. Our point of comparison is RTL check, which verifies a Verilog design preserve a manual return MICRO' model with respect to a suite of litmus tests. The result is following. The chart has y-axis being runtime in log scale, while x-axis is each litmus test. The left bar is RTL check's time to prove Verilog complies with MICRO' model per litmus test, where dash bar means incomplete proof. Stack on top of the right bar is amortized time of synthesizing MICRO' model, while both the bottom gives runtime of check tool evaluating a litmus test against synthesized MICRO' model. Amortized synthesis time is 7.33 seconds, and litmus test verification takes 0.03 seconds per test. RTL check, on the other hand, has an average time of 1.61 hours with incomplete proof coverage. Finally, there are some details missed out here, but discussed in the paper. For example, the paper described all processor design metadata required for RTL to MICRO'. We also discussed the scope of processor design that are currently supported by RTL to MICRO' and how RTL to MICRO' embed hypotheses in SVAs. Moreover, our paper featured an artifact evaluation with the instruction on how to run the tool. Finally, we find a new bug in multi-V scale missed by prior work. In summary, we propose a new approach and tool for synthesizing correct MICRO' models directly from RTL for efficient MCM verification. We achieve this by first defining what constitutes a complete MICRO' model, namely intra-instruction HBIs and inter-instruction HBIs, as rules for instruction execution path and instruction interaction respectively. Second, we develop an incremental MICRO' model synthesis procedure in which we enumerate all potential hardware events and interaction between them, generate hypotheses that will be proven or disproven by Jasper Gold, and include only those proven ones into the final correct by construction MuSpec model. Finally, we show the RTL to MuSpec synthesis MuSpec model can support efficient MCM verification with the check tools. Here ends my talk. Thanks for listening.